in Lab 4 on oscillations. So the energy principle states that the change in energy of a system is equal to the work done by the surroundings plus the flow of energy between systems and the surroundings, and that there is a cause and effect relationship between the system and its surroundings. We also know that energy is conserved, and that spring potential energy is 1/2 kx squared, gravitational potential energy is mgh close to Earth, kinetic energy is 1/2 mv squared, and the spring force is F equals negative kx. The objective of this lab is to explore the conservation of energy with the motion of a spring using an experimental model and computational model. The position data in the x and y axis can be used to determine the kinetic, gravitational, and spring energy. If energy is conserved, then change in energy of the system should be 0. So here's the video that was used. And as we can see, the spring is oscillating in the x and y direction. And here's all the code for reference, but I'll explain it more in depth later. But as we can see, this is the computational model. And here's more code. And then here it is explained more in depth. So as we can see, the mass of the object is 0.402 kilograms. The initial position of the object is negative 0.7 meters in the y direction, and the initial velocity of the object is in the x and y direction, and that was obtained by the initial first 2 data points using the tracker. And then we can see the initial time in delta t. The gravitational constant is 9.8. The spring constant, or the stiffness of the spring, is 6.83. The relaxed length of the spring is 0.123 meters. And then we calculate L, which is the position of the object minus the position of the spring. We calculate L hat, which is the unit vector for L. And then we calculate the total length of the spring, which is delta L plus initial L. And then we compute the system energy. And so we know that K equals 1/2 mv squared. Potential gravitational is mgh. Potential spring is 1/2 kx squared. And E is the sum of the energies. So here we set the initial of all the energies, including the total energy, to the values that we just computed. And then we know that gravitational force is going to be negative mg in the y direction, and then spring force is negative kx times L hat. And then the net force is going to be the spring force plus the gravitational force. And then we update the ball's velocity using the velocity update formula, which is velocity plus net force over mass times delta t, and update the ball's position using the position update formula, which is position plus ball's velocity times delta t. And then we update the spring's position, the spring's L hat, and the spring's total length. And then we calculate the energy changes. So we calculate the nu k, which is 1/2 mv squared, and then we do the nu k minus the initial k, the nu ug, which is mgh minus the initial ug, and then the potential spring, which is 1/2 kx squared minus the initial spring potential energy. And then energy is the final of all 3, kinetic and potentials, and then the delta E is the final minus the initial, which is the total change in energy. And so here we can see that the total change in energy remains around 0, and that all the kinetic energy, the gravitational potential energy, and the spring potential energy are all oscillating, and they all balance each other out to 0. So whichever one is greater, as we can see, the 2 potential energies are always on opposite sides of the axes. And this will be explained more in depth, but this shows that the delta E remains at 0. And then here's the position information from tracker. So as we can see, it's oscillating in the x and y direction pretty consistently. And it's pretty constant oscillation. So the results and observations, both graphs demonstrate oscillation and periodic motion with the shape of the graphs and the repetition. And the experimental and computational model both show regular oscillations, as can be seen by the position versus time graphs for the x and y axis. And we know that energy is conserved because change in energy is 0. So what does it mean? Is the energy principle satisfied? So the energy principle is satisfied because the change in total energy is always 0. Also, as can be observed, gravitational potential energy and spring potential energy always have opposite signs, and kinetic energy is always on the same side of the x-axis as the potential energy with a lower magnitude to create a total change in energy of 0. And then to check the periods of both the oscillations, so For both graphs, the period of oscillation is about 2 seconds for the x and y axis, which is consistent with the equation, which is period is 2 pi times the square root of m over k, because m, which is the mass, and k, which is the spring constant, would be the same values for the x and y axis. Thank you.